Hi, all. On this second unit, design of combinational logic circuits in CMOS, we're going to discuss about dynamic CMOS logic and domino logic in this lecture. It is a dynamic CMOS logic. So previously, you have seen static CMOS logic, right? Uh, which is, the meaning is called dynamic, which is changing between zeros and ones. That's right. The changes happen often, right? That is dynamic. Uh, we have previously seen ratioed circuits and static CMOS logic circuit, okay, transmission logic gates, fast transistor logic gates, everything I was saying, right? Why we are moving into dynamic logic circuit? The thing is, the ratioed circuit reduces the input capacitance by replacing the PMOS transistors connected to the inputs with a single resistive pull-up. In ratioed circuit, what you have seen that PMOS circuit it's grounded, right? PMOS circuit is grounded, or we can replace that CMOS circuits by a resistor that is called resistive load. If you are connected with PMOS, it's a pseudo NMOS logic. We have seen that the drawback of ratioed circuit includes static power dissipation. So that we have seen how we are overcome that static power dissipation using the CVSL logic circuit, right? So the main drawback is a static power dissipation. Okay, when the device it's in on, it's not operating to conduct. Okay, even though it delivers the it dissipates the power, that is called static power. Okay, and that is and a non-zero VOL, that is low output object, that is we represents VOL. Okay, so dynamic circuit overcomes these drawbacks by using a clocked pull-up transistor. In this instead of PMOS, okay, we are using clocked PMOS in the dynamic CMOS circuit. See, the same CMOS inverter, how it is looks like, the same thing happened in PMOS and NMOS, whereas instead of input, here we are replacing with clock, that is pi. That is a simple structure for dynamic logic gate. So pi represents clock and A represents your input. So whatever the logic you want to implement, that is given in the pull down network. So pull up network always be a clock. Okay, clock means we can have both on and off states. I mean, the graph says that the timing diagram pi, which represents when it is clock goes high and it goes low and goes high and goes low, like that it has happened. And according to that, your output will what the circuit which is available in the design, so based on that you are getting the output. Okay, so how this circuit will work, that is the simple operation. Here we have two modes of operation. One is precharge mode, another one is evaluation mode. Okay, precharge and evaluation. What is that precharge mode? So at that time your pull down network won't be conduct. So whatever your VDD has, that is charged by the capacitor. So here I didn't mention the capacitance value, that output of that Y, no, so we may have our own capacitance, so that capacitor will get charged. Okay, so when it happens, when PMOS is off, right, when PMOS is closed circuit, at that time only your VDD will flows through the PMOS transistor and capacitor get charged. That is pre-charge state. When that PMOS transistor off, that is turned off, which means closed circuit, when pi equal to 0. So that we have seen at the very first uh, class for this lecture, okay, in static CMOS design. When pi is equal to 0 in PMOS, that is PMOS is on, then Y is high. So PMOS is on means which is closed circuit, your VDD is directly flow through the Y, that is precharged mode. When pi equal to 1, clock equal to 1, what will happen, that PMOS is open now. Okay, so your VDD won't flow through this to output. Whatever already precharged value, that is flow through the pull down network. that is based on your A, that is based on your pull down network configuration. Whereas here only one transistor is there, that is input is A. For example, if input is 1, A is 1, what will happen? A is 1 means it's closed switch. So you are automatically your Y precharged value, it's getting down to the output, right? Right. In this, the graph shows that is the graph shows that pi, when clock is evaluation, when pi is 1, right? When pi is 1, that is open circuit in PMOS. So at that time, what is the configurations available in pull down network, that is evaluated by the circuit. When it is in precharge, when pi is 0, so at that time pull down network won't connect to the network. So your precharge happens, right? So that is the graph shows that high value, right? So like this, your precharge mode and evaluation mode work in the dynamic CMOS circuit. Then there is one problem in this dynamic logic, that is condension. What is that condension mean? When A is 1, at the same time pi is also becomes 0, right? So what will happen when A is 1, pi is also becomes 0. So both the transistor will conduct, right? So in the circuit, when pi equal to 0 means PMOS also open, and A equal to 1 means NMOS also open, closed. Both are closed. So at that time, your this won't happen the precharge state. So automatically your VDD getting short with ground, right? So this problem is called condension. If input is A during precharge, condension will take place between both the PMOS and NMOS transistor will be on. So when the input cannot be guaranteed, we cannot say that guaranteed to be 0 during precharge, and so that we need a extra clocked evaluation transistor can be added to the bottom of the NMOS transistor. That is called footed transistor to avoid the condension problem. I think you may follow the logic, right? When both the transistor on, the precharge state won't happen. So automatically your drain VDD, which flows through both the Q transistor and A transistor, will get the output. So this won't happen in a dynamic CMOS circuit. So that's what they have given a footed transistor. So now check with the first one, footed inverter. When pi equal to 0, what will happen? PMOS is conduct, and NMOS, foot NMOS is what? Foot NMOS is 0 now, right? So because in this NMOS 0, it's open, and PMOS 0, it's closed. So automatically there is no short between both the, even though even A equal to 1, so there is no short between drain and uh, ground. Okay, so it should be avoided. So that is footed dynamic logic, right? And whereas in dynamic, this is dynamic NAND gate, and followed by footed dynamic NAND gate. So in bottom of your pull down network, we are just adding one extra NMOS transistor which is clocked. So that is footed transistor logic, footed dynamic logic. Okay, so what is that dynamic logic? To avoid the static power dissipation in ratioed circuit, so we are going with the clocked pull up transistor in dynamic logic, where we have two modes, precharge and evaluation mode. And to avoid the condension problem, we are making as a footed transistor below the NMOS network. Okay, right. Then another one is domino logic. What is that? Domino logic. So simply we can say that along with dynamic logic, we are just adding the inverter. So that is domino logic. So you are getting the inverted output. So your inverted in generally we are getting inverted output that should be complemented. Non-inverted output we are getting. For example, so domino and gate is there, no? We are getting domino and gate. So whereas in previous domino dynamic NAND gate we got the output for the first stage W. So after that I am giving one inverter circuit that is giving your A dot B. This will avoid the monotonicity problem. What is that monotonicity problem? The dynamic and static pair together. Okay, monotonicity occur during evaluation mode. For example, the graph shows that the timing diagram A. So my A input is down in between the evaluation mode. Okay, so what will happen? Automatically your Y tries to get the high value. Okay, Y tries to get the uh, high value, but it won't be happen. Okay, it won't be happen. So it will give after your evaluation in the during the precharge value only it has to be high. Okay, so the sudden change in the input during the evaluation state, the monotonicity problem will happen. Okay, to avoid that we are using one extra inverter circuit at the output terminal of dynamic logic gate, that is called domino logic. Okay, whereas here W and Y it's, parallel sequentially are getting the outputs. Okay, that's an example of domino of OR gate. So we know that this is the configuration for in second diagram, below diagram shows the dynamic NOR gate that is connected with one NOT gate which is giving you a OR gate, right? The domino OR gate. So I hope you understand what is dynamic logic and domino logic concept. Thank you.